Good morning. Welcome to the DeviceTree BoF. I'm Rob Herring, if you don't know me, and I'm one of the DeviceTree maintainers. So the agenda for today is talking about Json-schema for DeviceTree bindings, and then Linus is going to talk about connector bindings. So this is kind of an update from 6 months ago. There was a session that Grant likely led at Connect in Hong Kong, and I stole these slides from him with his permission. But so what is the problem? It's easy to get device trees wrong. There's no validation that what you write for the binding matches, or that the DTS matches that. And it's very much a manual process of reviewing the bindings and DTS files, which I have the joy of doing. And device trees can be a steep learning curve, and it makes it hard to get things right. So what are the goals for this project? We want to define a language for writing bindings that's human readable but machine parsable. Have better tooling so we can validate DTS files. And I don't want to write a language, so we want to leverage existing technology. So just kind of recap what was talked about in Hong Kong, where we're at. There's a link to the session if you were not there. So we're using Json-schema as the vocabulary. The schema docs are actually in YAML format in a JSON-compatible subset of YAML. And the tools are written in Python using YAML and Json-schema libraries. So who here has heard of or is familiar with Json-schema? Not too many. So this is status, kind of what's happened in the last 6 months. We kind of had some initial concepts kind of working 6 months ago, and I've been working on improving that, expanding it, and getting it integrated into existing build systems. So now you can pip install the module straight from GitHub. That installs all your dependencies. As of last week, DTC now supports YAML output, with the caveat that it's used for validation. The format could change, so don't expect it to be stable. I've also improved what we can validate using schema, adding support in for size types and p-handle tags. That's part of the DTS input, and that gets maintained through the YAML output. I now have it integrated into the kernel build system, so you can validate all the binding files against the meta schema, and then use those along with the core schema from the schema project, and validate all of the DTS files in the kernel against that. And it's taken some work to get the performance there to be somewhat reasonable, but it's now at a manageable point. But we don't have all the bindings converted, and I worry that when we do, it will be slow again. So this is what the flow looks like. So the green boxes are files that are in the kernel. They don't have to be, but what I've been working on is it's all the kernel files, and that's the majority of DTS files. The yellow is schema files. That's kind of all the core bindings, things like reg and compatible and interrupts and GPIO just, is partially there. And meta schema is the schema that checks your binding documentation. So there's two new make targets, DT binding check, which will check all your documentation schema. That outputs a process schema. So we do some processing on the schema to kind of cut down on some of the boilerplate of what you have to specify in the documentation. Then the output of that is used to validate the YAML encoded DT file that DTC is building with the DTB's check target. And then you run that and you get thousands of warnings. So going into what the schema docs look like, this is kind of the list of top-level keys in the document. I'm not going to go through every one here, but all but maintainers and select are standard Json-schema keywords. So the kind of the guts of the validation schema is under properties or pattern properties schema. This is typically a list of all DT properties for a given binding, and can also be child nodes in some cases where a given binding has child nodes. Example of this is CPU's binding for ARM, and then under that has CPU nodes. And then there's kind of two different ways of how you describe what you need to describe on properties. For common properties, there's less that you need to describe. Vendor-specific properties that the core doesn't know about are slightly different. So here's two examples of some common properties. So in this case, the core binding for like for clock frequency defines that its type is an integer, and in the device-specific binding, you just need to say what's the minimum maximum range, or if you have an exact target, you could specify that with a const property. And then for reg, we know what reg is. What we don't know for a given binding is how many of them do you have. So, and what is each item. And so you describe it as 2 items here and the description, and you're kind of inherently describing that the length is 2, and that's part of the boilerplate that gets added in when you run the actual validation. Now, vendor properties look a bit different. So the core schema is going to know nothing about the property. So we have to refer back to generally what is its type, and that's done with a reference and the $ref, and that refers back to a definition in the core schema. And then there's the way you, in JSON schema, that you kind of subclass things is the using the all of property at the top there. And so you're saying it's uint32, and then it also has these other properties. And then a string property is similar. So lessons learned and gotchas from having worked on this. First is YAML is indentation sensitive, and it doesn't like tabs. So it's kind of a combination of Python and Make, I guess. And and Json-schema keywords are case sensitive, which would be easy to trip over. We've kind of mitigated that with the meta schema. And the other big issue I've found with JSON-schema is that unknown keywords are the default behavior is just to ignore them. When you combine that with the one before, that's not a very good behavior. And it's also tripped me up if you have stuff in the wrong place, particularly with like items schema. And some of the validators have modes where you can turn that quote feature off. Unfortunately, the Python library currently does not. One key area I haven't figured out how to address is how we handle interdependencies between different properties. So the example is that I've seen several times is like if it's compatible A, we have 2 interrupts, or if it's compatible B, we have 1 interrupt. And right now that's just free-form text, and there's not really a way to describe that in JSON-schema. There's discussions in that community about how to do that kind of thing, but no solution yet. So for now, we're probably stuck with what we already have, which is free-form text. Or we have to go split. In this example, we could split the bindings. The other annoyance is if you add levels in to do using how you do combinational logic, which is all of, one of, any of keywords, that results in the library giving you very vague error messages. Essentially, it's this does not match any of the schema. It's not too helpful and kind of hard to dig down into. Final one's kind of this, generally it's 1 binding per doc, and in some cases we've combined multiple things in the document, so that's just some restructuring we have to do.
That last one on 1 binding per doc, that we should be able to solve easily. We're already not using the JSON-schema file format. So to have multiple a YAML file with multiple sections for multiple bindings.
Yeah, I thought about going in and supporting that, but you kind of, the YAML calls, I think you have to know that, what the document has, and it seemed to complicate things, and I think it's better if we split it out, probably, unless maybe we're addressing the one above that or the constraints, the interdependencies of properties. Those we may want to keep in one document, but like the example I've found is I've done a lot of the top-level board bindings and converted those, mainly because they're easy, but people have stuck like system control registers binding in with it, and it makes sense to split those out. Any comments on this or questions?
You're looking at me. So I think I asked this back in Hong Kong, but kind of the same question again is about how to describe dependencies about parents, right? And it's things like, you know, I'm a sensor and I expect to be on an I2C controller, right? And so, you know, that information is sort of implied today, but we don't have any way, it's not spec'd anywhere. And then obviously there's cases where we have, I know I've seen sensors that could be either on I2C or SPI, so you have to kind of deal with that as well.
Yeah. I need to think about that. Maybe we want some top-level property that says this is a I2C device, or
Yeah, it should be fairly straightforward to do the one direction of making sure all the children are of a certain type, because it's easy to put those constraints in. There had been some talk in the JSON schema of being able to go back up the tree to make sure that things, it's a little bit harder. We can define custom properties. Like, so the nice thing about JSON schema is that it gives a vocabulary, but that vocabulary isn't exhaustive. We can do device tree specific things in there if we need to.
And I've done that in a couple of cases. But I've generally tried to avoid doing that. So the two cases I have now, well, for one, they're in the core schema and isolated from the device bindings. It's the type size, and so it carries the bits 8 or 16 tags through to the YAML, and then validates type size, and that gets defined in this reference to the UINT32, or there's a UINT8 and a UINT16. And the other case is p handles, and I quickly put something together. I need to think about it some more, how I've done it. But reviews on both of those would be great. Grant?
I know.
Okay, so how do you run all this? So a lot of the work I've done in the last 6 months is trying to make this easier and painless and something that we can merge upstream. So you can now just do a pip install of the Git tree directly. The deprecated process dependency links option is needed, and it doesn't seem there's another solution, but I don't really know Python.
Rob, what is pip? Is it like Python package manager?
Yeah. And
There's no plan of putting that stuff in the kernel or anything, you like the DTC?
that's coming in another slide. Right now it's not. You can also check out the repository and run setup.py develop or install and install it that way. Then you need libyaml and its headers. Then it's just you configure your build, run to build the bindings, DT binding check, or to build the DTBs and check them, you can DTBs check. Until last week, you needed your own DTC. In 420, you should not need that.
Does it come with memory?
Yes, it matters. But yeah, you have to configure the kernel. I use all mod config because that turns on building all DTBs because it sets compile test, and you can run all that in one step as well. DT binding check is a dependency of DTB's check. So just going to go through a demo of that. So I have my kernel tree. This is 2.6. That's how old my tree is. So I already have the project installed. So it's going through all the YAML files that I've converted, and these check DT entries, they're all passing the metaschema check. And then another feature I've added is the examples now get compiled. So we extract the example out of the schema file and build it with DTC, and it just takes a few wrapper lines to get that to work, and also building it as a overlay, so p handles don't have to resolve, helps make it work.
So that means you can sanity check all the examples with this thing.
Right, and that's a common source of typos and other problems.
Awesome.
Right now, it's only doing checking with DTC, which if you've noticed warnings coming in, there's a lot more checks in DTC these days, but really we need to make that use the schema to check the example in the schema, but I haven't gotten to that.
Is that for many bugs? You actually fix those schemas themselves?
I think there were a few things I had to fix, but in reality is most of these are empty examples, so it's just building the boilerplate. But I know like the CPUs binding and the timers have examples. So I'm going to build check all the DTS files, and it's getting a mixture of DTC warnings because this version is not completely clean. It's not terribly slow, but not terribly fast.
Well, you can see here that the bottom of the entire definition is some regular expression things that's coming from the very lowest layer of it.
Yeah, one thing I've learned in the project is it turns out that the spec says the maximum number of characters for properties is 31, and we've never checked that.
I think we might fix that by changing the spec.
That seemed to be the consensus. So if we go back and so we're getting a lot that are just core schema, all these memory. So like this is an interesting one. This one's interesting because this is likely that one of the compatible strings is not documented, or that having all four of them is not documented, or something like that. but it's pulling this from the at-mill board level binding document. And this is the less useful error message. While some of them are and let me pull up one of the binding files.
So the error messages that are being output here is pretty much the raw error that is output from the JSON-schema library. It's pretty ugly to look at. There's a lot of data in the objects that are created, so we can clean that up quite a bit, and we're going to need to for it to be, usable for developers who don't want to know the details of JSON-schema.
Well, most of it's pretty in better state than kind of their default error processing it, other than where you have the combinational stuff. So this is ARM CPU's binding that I converted. And a lot of this, I've written a script that kind of can partially do the conversion for you. So it fills in the ID, the schema. Title is extracted from the first line of the binding document. Maintainers is pulled from the get maintainers. It's not perfect because I had one binding that Linus was the maintainer, not you, the other Linus. But and then the description is the text pulled out. And I may have edited this one, and it can't do the properties, but so that's the manual part of it. So then here's an example of where you have a child node with pattern properties. Under CPU's node, you have CPU at and some unit address, and then within that, then you have properties again, and the properties of that child node. So that's it. So kind of next steps. So the YAML support for DTC just went into DTC master last week. I've been working on putting that into the kernel version, and there's some rework I'm doing in DTB building, and that this is all dependent on essentially moving all the build targets that are in each architecture out of the architecture into the top level makefile, because every architecture was doing things similarly or slightly different, and some supported DTBs install, some didn't. Some could build all DTBs, some couldn't. Then there's figuring out what to do with the YAML binding project, whether to keep separate or integrate a subset of that into the kernel. I think I'm leaning toward the first one, because I think then we can iterate more on that and improve the core bindings independently of the kernel. And then converting bindings, help wanted. So I've done some of them. I'm not doing all of them. There's 3,000, I think. And we need to do some of the more complex ones. So come to me with your complex cases, and we'll look at how to solve those.
Yeah, well, what I think we need is like just a pointer. Like this is how a good converted binding looks, and here's another one, and here's one for this case. And if you fall in these categories, it's pretty automated. You just need a brain, I think.
Right. So, well, there's the pointer. So the GitHub project has information on how to install that project and some description. The kernel tree, the branch I just showed is up there, and it has. I've started a writing schema document, how to, so that's in that tree.
Maybe you should just put it in DT bindings in the kernel as like a how-to document or README or something.
Yeah,
so
that's what
people
it
can
is.
find. Yeah, that's the one. All right, good.
It's just under documentation, device tree, writing schema, I think.
Perfect.
Make sure there's a copy of that maintained in the DTC tools as well, because we're Zephyr and FreeBSD, and of course UBoot are all going to care about that. So.
In DTC or in YAML bindings?
How confident are you? How comfortable are you with the way things have turned out with the YAML file format?
I think it works well. The only issue I've had with it is what do we do with the examples? Because we can't have tabs, and do we reformat them all to 8 space indentation, or what? Because we're doing 2 spaces for the rest of it. And
oh, I see what you mean, just for reformatting.
Yeah.
Well, I mean, there's still a whole bunch of this stuff that ends up being freeform text. So, I mean, I would say if you're converting, just doing mechanical conversion over, you do what's the easiest to get us through, to get us over all the DT files convert over, because they're not finished. These binding files are not going to be finished for a while, but
Right.
It's not like source code in the kernel. It's not going to break the entire kernel build. We can. I'm pretty comfortable that the layout of the YAML binding files is sufficiently good to just say that's our binding format now. And if that changes, it'll actually be easier to do mechanical transformations once we're in a YAML file than before we are, or even to parse over them and find everything there. So I would say if we're putting them into the kernel tree, which we can probably do now, then put the documentation for what the YAML binding file is into DTC.
So when do you say that new code requires schema to bindings? When is that like what point is that cut occur?
Probably a cycle or 2 after we can actually have YAML bindings. And I think it probably won't be a hard cut over, because I'm not going to tell people, oh, can you change your V10 patch set to use YAML? But with it in DTC, that's the only thing, well,
Fair enough.
it has nothing to do with the YAML output other than we use it.
You're,
But I
fair
was
enough.
about to say
Fair,
it's the
fair
only
enough.
YAML thing.
Put it in YAML bindings. That makes sense.
And that will get copied over into the DT-only tree that we generate anyway.
So, any plans for packaging the tools? I know their YAML bindings are still under active development, but it would probably, I guess, be worth looking at so that it's more likely to be at least somewhat available by the time we actually want to cut over to using it as the only way forward. And it'll make it a lot easier for people to keep up to date and not be using an old YAML bindings or whatever.
So you mean like Debian packaging?
Yeah, or I understand other operating systems are available, but yeah.
Well, and there's pip packaging as well, in addition to direct from Git. I don't have any plans. I barely know what I'm doing with Python, and
Yeah.
I have done some Debian packaging, but don't really care to do both of those.
Yeah, I mean, what we did for the core site decoder library was we just talked to whatever builds and baselines is called these days, and they were able to help out with it. So I guess something like that could happen with this as well.
I think ultimately the goal should be integrated into DTC once, have a fairly high confidence that it's the majority of the functionality is there. There's also a bunch of the way that it's implemented now, which is kind of naive because it's DTS files, converts to the YAML, and then the main reason why there's the YAML step on the files is because that made it super easy to write the Python script to load up 2 YAML files and smash them together and get a result on the other side. We have Python bindings in DTC. It would be very possible to have that libfdt interface into Python, where we go DTS file straight into the validator. And when performance is a problem, there's places that we can do that to improve the performance of the whole thing. What's that? Yeah.
Yeah, if we go that route, then you wouldn't be using any Python package infrastructure.
Depends on which way you did it. If you had DTC calling out to Python. If we continue to use lib Json-schema, or sorry, the Python implementation of Json-schema. I'm not particularly interested or excited about switching to another Json-schema library. But if someone really got a bee in their bonnet about doing something 100% C for Json-schema validation, that is an option. One of the nice things about it having a spec behind it is that there are multiple implementations.
Right. And performance-wise, I'm not sure how much we can do there, because we're for each node, iterate over each schema and decide whether to apply it or not. And you can't.
That's one of those ones we should. There's some natural optimizations that we can probably put in, such as having schemas looked up by compatible values, and that would reduce the amount of churn. It would reduce the order and squared complexity.
Right. Anything else on DeviceTree schema? So next up is Linus. He's going to talk about connector bindings, which has been another long-standing issue, I guess, and there's been some progress there. GPIO Nexus binding has gone into the spec this year, which is how we expect to do GPIO through connector. That's one area that's been worked on, but I'll turn it over to you.
Yeah, I don't know. I think it's more BoF than I talk. because I need input, or we need input, I guess. So for you who don't know what this is, these are the mezzanines and capes and other daughter boards, whatever you call them. They are plugged into some reference design usually, but could also be one of those stacky things for actual one-off products or few-off products that are made for, say, your particle accelerator or something like that. People build them up with a base board from some SoC vendor, usually Freescale or something like that, NXP nowadays, and then they put like this on top. Xilinx have the same thing, and for all the maker community, it's usually this Beagle bone capes, and for the 96 boards, which are somewhere, in my mind map, somewhere in between product development and maker community, there's this mezzanine. They are sometimes discoverable, and then the problem is solved because there's some EEPROM you can ask. You always know where it is. You don't know which I2C address it is on, for example. That's crude but equivalent to, say, PCI's config space. So you can ask the device, what are you? And then you can instantiate it from, say, 16-bit or 32-bit number or some identifier or string or something like that. That's awesome. If you do any daughter board connector thing, please, if you're working in a standard committee, put that into your specification. However, for the mezzanines, there was nothing like such in the specification. It's also a cost issue, of course. You have to put an EEPROM there or something, and that costs money. So some of these are not discoverable. You just can't ask them with a I2C or something what is on that connector. You just have to tell it somehow that you have this daughter board. And what we have done for the few cases we already have in the kernel is just make -variant A, -variant B on the DTS file on the top level and just put it in there on the I2C channels and so on, whatever it is. That's not very elegant. So people want to use DeviceTree overlays for this. And that is essentially you can insert an overlay either in the bootloader or from user space in the kernel. And then plop, it populates the daughter board, branching off from the I2C and GPIO and so on. And the GPIO Nexus thingy that Stephen Boyd put into the GPIO subsystem, and I merged, what it does is essentially create a local number space on the connector so that you grab your GPIO line from that number space instead of having to refer back to whatever GPIO controller it's on. So it's just like you go here and then from there somewhere else. It's a Nexus, it's nice. Nexus is Greek for connection point. That was the idea with that. Then we have the developer box. And the developer box, Synquaser, it's using DeviceTree. You can boot it with DeviceTree, comes up, very nice. And the vision of some of the people there is that it should also be an enterprise or desktop product, and enterprise and desktop products use ACPI. So screw them. That's sort of no, that's not my value. It's just like the stance of the DeviceTree effort to handle non-discoverable hardware or daughter boards is sort of like, if you have another hardware description language, that's your problem. We are not going to solve it for you. And that's not really as kernel developer, I get pretty confused when I get into this situation because the first thing that happened to me as a subsystem maintainer, and now I'm just like rambling about my feelings, is like first somebody tosses DeviceTree on me and say like, now you are a DeviceTree binding reviewer. Okay, thanks. And then a few, two years down the road, I get mails from people working with ACPI standardization and say, Naki, now you are a contact point for advisory for ACPI people. Yeah, okay. And now there is a discoverable daughter board. And yeah, we are going to do that two totally different ways, and you are going to be the question and discussion point for both. And that is actually that becomes a little bit strainful. So because these device tree overlays, they have a very complicated roadmap, at least if I read Frank Rowan's notices on it, and quite a lot of work. And I don't even want to begin to imagine what that would mean for ACPI people to do the same thing. So I just tossed up my hands and wrote a bus in the kernel that sort of populates this thing with like a board file. I know board files are bad. It's like GoTo in BASIC or something. Really bad, don't do board files. But end of the line is it solves the problem to reuse the same description of that board for DeviceTree and ACPI, and that's why I did it. So it just grabs the GPIOs routed to that node with that it's not using the Nexus or anything like that. It just grabs them and uses them. It grabs the I2C, it grabs the ASPI if you have that. And it's a proof of concept. I think Frank said he hates it, or he didn't use that word, but he said knack. So I understand that stance. What I feel as a subsystem maintainer is maybe, or can't we do both, or can't we just try to find some common ground here? I guess one option would be to say device tree overlays, actually ACPI should use them too. But I don't know how that would work in a practical context. In theory, I bet it works. And this FW node thing that Rafael and Mika and those guys have been going on with, and also Dmitry Torokov, I think, they are very much abstracting ACPI and device tree away from the kernel and trying to hide it behind something called FW node. It works a bit so-so. So please share your thoughts about this issue and what way forward you think is right. Rob, you have all attention now. Please go ahead.
So there is a related use case, I guess, for DT on ACPI systems, which is where you have things downstream of discoverable devices. So example that keeps coming up is like a FTDI USB to UART or SPI or I2C or GPIO device, and you want to describe all the downstream connections of that chip, yet it's on USB and it could be plugged into any USB port and could be plugged into your PC, which is not device tree. And I don't know if we could do something, we don't have a solution, but maybe there's something similar could be done here. I don't know.
I remember Matthew Garrett mentioned something like that about the Macintosh mouse on PowerPC, which he plugged into a PC, and out comes a DTB. Yeah, nice. It was plugged into an ACPI system, so he could use that to describe the stuff that was out in the mouse, for example, or whatever, scrolling properties or things like that. So that would be an option, but yeah, I don't know how resources on the ACPI side would map nicely to some device tree fragment on a device, if it's just pie in the sky or if it's actually doable.
So I'm still struggling with how this actually works for binding devices to drivers behind the connector. So I can see how it works for GPIOs. That's fairly obvious. For an I2C device, how, like we have a daughter board that has an I2C device on it, and we have a driver for that I2C device. And now we have a connector, and we know that there's this device on this bus. But how does your code connect the two?
What it does right now is just put in a P handle, and then the subsystem has a hook to get a handle on that bus. So it's just code. And then I just populate on that. I get a handle to the actual bus in the API from the subsystem, and then I populate the devices onto that bus. And I think Rob said that alias is probably better to use than P handle. I don't know the difference, so but maybe.
Yeah, kind of binding-wise, there isn't a way yet, and we've got to figure it out interface by interface, and so far we've figured out GPIO.
For some reason, GPIO is always first. I hate it.
I'm not going to claim deep expertise in ACPI, but I kind of felt that the philosophy of saying this is the connector and the thing you plug into a connector has an ID, that's very much in line with the ACPI philosophy, which is essentially the PNP, the old school ISA PNP IDs extended 3 times. So to be describing the ID of the board you plug in and have to figure it all out from that ID is very much the ACPI philosophy. So it's very compatible with ACPI. Well, I'll get disagreement, but less so with DT. So
the way practical industrial systems I have worked on seem to do this on ACPI is that they have the DMI ID for the motherboard, and you, in principle, match on that. In practice, you never bother filling that in production, so you just shove a driver in there and hope you install the driver on the right system. So it probably matches or it does somewhat match the ACP idioms, but it's not practically something people working on systems, on ACPI systems that actually have this problem are doing. They're following pretty much definitively worst practices for the most part.
I mean, without question, a non-discoverable bus is worst practice, but the problems would actually be pretty much the same if the bus were discoverable. You'd still, if you had an ID you can read like you do on a Raspberry Pi, the problems don't actually get much simpler. It's just you know the ID in advance where you didn't before.
Yeah, on those systems, or like on modern x86 laptops with audio support. It's the way they're doing it is load something based on the DMI information for the baseboard, and if you could enumerate the audio subsystem, it would be the same thing, and then you just have platform data based on that information.
And that explains, like, I think we had a discussion, like, it's maybe not always such a good idea to start to remove platform data. I'm guilty. But it actually might have a good utility, especially for devices that are shared between DeviceTree and ACPI. Especially if they use heuristics like that to populate them.
Yeah, it's astonishingly good. It's amazing.
So any suggestions? What should I do next step? Should I try to put a device tree fragment into an ACPI system? Oh, Tony's there, sorry.
Can't you make it the driver? Can you make it the driver and probe it early? Like, why do you need to do a board file?
It's more or less what I'm doing. It's a driver for that daughter board. That's what I do. And that driver populates the devices on that board. And whether that board is then discovered from, like you have the connector, and then you have a node below it that has a compatible IM daughter board so-and-so, which would be equivalent to ACPI ID or something like that. That's at least the way I think about it, unless my mind map is wrong. So if you have that, you can just populate. But it is a board file just for that daughter board.
Okay.
I wouldn't try to hide that fact.
Yeah, thanks.
Yeah, I don't see any problem with that. There is lots and lots and lots and lots of precedents for if you can identify that device. I mean, with the board files, we had the problem of we didn't even have identifying which board you were on, where that kind of flip over point is whether or not we need to have a large amount of variability on the back end of that connector. I think there's so for a lot of the things that you'd be plugging into 96 boards or into where there's a bunch of functionality, or you're doing some larger system development, where it's not just a trivial couple of devices, but you've got something fairly big, then I can see some value, especially if there's like no pop options. But it's hazy between those and I don't see any particular problem with if you're able to identify the board and it makes sense to have a driver for that board, to do a driver for that board.
So that's pretty much what I did, but I think the controversy comes when I put the compatible for that board, and they say like, yeah, I'm just going to populate it with this driver board file, whatever you want to call it, and not use the device tree overlay, because people who like device tree overlays get very sad when I do that. You see the problem here? This is like a little, I call it an imperialistic ambition, and maybe that's a bit harsh, but it's like, but what about my nice device tree overlays? I like them so much. It's a little bit like that sometimes. And this was going to be the school example of how you do a nice device tree overlay, so I do understand them.
To take on that argument, we've also got lots of precedents on where we prefer to get our information about hardware. The whole reason device tree exists is because hardware is dumb. USB, PCI, well, USB doesn't use ACPI. We've got ACPI that's used to describe the PCIe, or sorry, the USB host controller when it's not wired up properly. But USB, it's a bus model. We can detect what hardware is on there. We prefer to get information from the hardware rather than just have everything described. PCIe, you can probe, you can get all the information with the hardware, and then PCs go, oh, but this one's broken, so then it will add some ACPI. But the ACPI is an addition to solve additional problems as opposed to being the primary mechanism. If you've got a primary mechanism that will detect the board, I really don't see a problem with that.
We don't have that for the Mezzanine, so.
We're out of time, I think.
Okay.
So
Hallway discussions.
thanks for coming.